Hi, and welcome to Module 4 of Lecture 6. We're almost ready to start computing actual maxima and minima, but first a couple more definitions to get us a handle on what's going on and what we'll be doing shortly. The first is a definition of a critical point. A critical point of a function is any point at which either the derivative of the point x star here would be the critical point is 0, or the derivative at that point does not exist. This means exist, this means does not exist. So, does not exist. Really, they should be put before that, but whatever. So either the derivative is 0, or the derivative does not exist. Why do we care about critical points? We care about critical points because local maxima and minima, local extrema, occur at critical points. So those are why they're important. Now, in general, here, there's going to be kind of special cases when you happen to have a function going off to infinity or going off to infinity negatively, somewhere in the middle of the function. Usually what we're going to care about are things like this, and these are known as stationary points. Since the slope is 0, in a sense, the function is going nowhere at that point, even though it could be going somewhere around the point. So these are stationary points. These points in which the first derivative is 0. And these are the points we're going to concern ourselves with for all the reasons we discussed already. Now, sometimes these points are going to end up being extrema, local minima or local maxima, local extrema. Sometimes they're not. At times when you have a shift from a concave function to a convex function, or a convex function to a concave function, these are known as inflection points. An inflection point is one where you shift, in general, an inflection point is one in which you shift from concave to convex or vice versa. Some inflection points are just points that are not stationary points. So for instance, this should be more vertical. Here you're shifting from concave down here to convex up here, but you're never actually going to 0. So the inflection point is not a stationary point, so it's not a big deal. Now, in this case, we don't have to worry about inflection points because we don't care about non-stationary points, non-critical points. But there will be times when you have stationary points that are also inflection points. We've dealt with one already, and I shouldn't have drawn that particular picture. Let's do it like this. All right, this was x cubed, and the point x equals 0 was both, we saw, a stationary point in that the first derivative was 0. The tangent line right here is flat, has 0 slope. And this is also an inflection point because over here is concave and over here it's convex. So this is an inflection point, and we see when that happens, when you have an inflection point at a stationary point, you do not have either a minimum or a maximum. So we have to be careful when addressing these things to see whether or not you have a minimum or a maximum or an inflection point. So a stationary point is going to be either a minimum or a maximum or an inflection point. That's all you really need to know now. What we're going to do next is form a rule. We'll start forming a rule for computing maxima and minima by first checking to see if it's a stationary point, and then checking to see if it's concave around their point or convex around their point, or neither. If it's neither, or rather if the second derivative is not going to show that, we have to go to higher order derivatives to check to see if it's an inflection point or not. And that'll be the whole rule. That's all that's to it. We've already looked at all the component pieces of the rules we're going to deal with, substantively, conceptually, right? We drew pictures like this that say, if you have a function like this, then this will end up being a minimum. We're looking for convexity around that minimum. Like this, it'd be a maximum up there. We're looking for a concavity around that maximum. If you have this, it'll be an inflection point, and we won't want to consider it as a minimum or a maximum. That's all we're going to do. We're going to translate what we just talked about in words into a set method for computing minima or maxima. The only other word you might see sometime is a saddle point. A saddle point is a stationary inflection point. They call it saddle points because in 2 dimensions it looks like a saddle. You see like this, or like this. It's an inflection point, but in 2 dimensions. You won't see that much in 1-dimensional calculus, but you might see in 2-dimensional calculus. The upshot of a saddle point is it's not a maximum or a minimum globally in all the dimensions at once. It has the same general characteristic in that it's neither a maximum nor a minimum, as does an inflection point. Thank you very much.